let's try an example here. We're going to find the intervals of concavity and the inflection point. So we're going to do it all for this function f of x equal to x raised to the power 4 minus 4x cubed. All right, so let's go through the process. Step 1, we actually want to find the second derivative. Let's calculate it. So we have our function. To get the second derivative, we need to just differentiate twice. So to get the first derivative, we get 4x cubed minus 12x squared. And then our second derivative, we just differentiate that. So power rule on this 4x cubed gives us 12x squared. Power rule on this negative 12x squared gives us minus 24x. And there's our second derivative. Not too bad. Now we want to do something with this second derivative. So we know the second step here is going to be figure out where the second derivative is 0 or figure out where the second derivative is undefined. So that's the second step. We actually want to set this second derivative equal to 0 and solve for x. And we actually want to look for where the second derivative is undefined. So usually we want to try to just get into the habit of just simplifying the function as much as we can right away. We know we're going to be working with this thing, so try to simplify it as much as possible first. And there's not too much to do here, but for the purposes of solving an equation, usually the factored version is going to be nicer to deal with. So let's just factor this. So the first term has a 12x. The second term has a 12x. So we can actually factor out a 12x. And when we do that, we have an x minus 2 left over. So usually that's one of our major little strategies here, is just see if you can factor this thing. And we can. So we get 12x times x minus 2. All right, so now we want to look at where the second derivative is 0. So we're going to take this equation, or take this function that we have, and we're going to set it equal to 0. And we're going to solve this for x. And because this is already factored, what we can do is we can take each of these individual factors and set them equal to 0 and solve for x. So we get 12x equal to 0 and x minus 2 equal to 0. And then we just keep solving each of those. So solving the 12x gives us x equal to 0, and solving that second equation gives us x equal to 2. All right, so this is where the second derivative is equal to 0. We took our second derivative, we set it equal to 0, and then we solve for x, and we got two solutions here. Now, for our second derivative being undefined, well, the only way something can be undefined is if there's division by 0, or maybe natural logs, or even root functions. And we're not really seeing any. This is a polynomial. The second derivative here is a polynomial. Our original function is a polynomial, so it's always differentiable. So there's no contribution here. And the reason is because this is a polynomial, so it's always differentiable. Or always twice differentiable. This function's always, the second derivative is always defined. All right, so what we've found here, these two x values, these are the possible inflection points. So we call these the possible inflection numbers. This is where this is where our graph might actually have an inflection point. There's a few things we need to check. So, these might not be actually where we have inflection points. There's more we're going to do. But just to keep that in mind, these are the possible inflection numbers. This is where something interesting might happen. And we need these for our sign chart. So that's what we're going to do next, is we're going to set up our sign chart. So we're going to do our sign chart for f double prime. All right, so how is this going to work? Well, those x values that we just found, 0 and 2, they really split up the domain of our original function into kind of 3 different intervals. So we're going to draw our number line, and we're going to plot those. We're going to plot those x values. So we found x equals 0. We found x equals 2. And then let's just write out the intervals that those x values kind of give us. So we have everything from minus infinity to 0. We have everything in between, so 0 to 2. And then we have everything from 2 to infinity. So we're just kind of setting up our sign chart here. And the first step of that is to draw in our domain. This is the domain of our original function. It's all real numbers, so we're representing it as a number line. Plot the 2 values we found from before, so those are the possible inflection numbers. And then figure out what the intervals are. And so what we're going to do is think of these are like these are going to be the columns. And then the rows that we're going to use are the different factors that we found for f double prime. So let's just list our different factors here. We have 12x, we have x minus 2, and then that's everything. So we're going to use that to figure out what the sign of f double prime is, and then we'll use that information eventually to figure out, well, what is the concavity of f? All right, so let's start filling in. All right, so let's start with this interval from minus infinity to 0. And what we can do is we can just pick a test number somewhere in that interval. So -1 works. -1 is in this interval. And what we can do with that test number is just plug it into each of these different factors. So when I plug -1 into this 12x factor, I get -12. I don't really care about the number. I just care about the sign, whether it's positive or negative. So we're using test numbers here just to help us. So I'm getting a negative here when I plug -1 into that 12x factor. Well, what do I get when I plug -1 into this factor? Well, I get -1, -2. I get -3, which is also negative. All right, so on this interval from minus infinity to 0, I have a negative term times a negative term for my second derivative. And that's going to make it positive, a double negative. And then I just repeat this process for all of the other intervals. So I have this interval from 0 to 2. We want to pick a number that's somewhere in that inside that interval. So pick something that's easy to work with, maybe like 1. It's always a good test number to use. If I plug 1 into this 12x factor, I get 12, so it's positive. If I take t equals 1 and plug it into this factor, I get 1 minus 2, which is -1. And I just care about the sign, so that's just negative. And because my second derivative here is 12x times x minus 2, I have a positive times a negative. So the result for this interval is negative. And then I just go to my last interval here, 2 to infinity, pick a test number, make it easy to use. So 3 is perfectly good. I take that test number, plug it into this 12x factor. I get positive 36. Don't really care about the number, only that it's positive. Take the same test number, plug it into this other factor. I get 3 minus 2, positive 1. So positive on that interval. And now I have a positive times a positive, which means my second derivative is positive on that interval. And there we go. We've filled in as much as we need to on the sign chart. Now we can actually say what the original function is doing based on this information. So when our second derivative is positive, our original function is concave up. So same thing over here. And then when our second derivative is negative, it means our original function is concave down. And there we go. We've identified the intervals of concavity. So we're just going to write out our result here. The original function f is concave up on the interval -infinity to 0 and on the interval from 2 to infinity. And then f is concave down on that middle interval from 0 to 2. Yeah, so we were able to identify the intervals of concavity. Not bad. Well, if we also wanted the inflection points, we have enough information now to kind of go back. We know our possible inflection numbers. These are where we might have an inflection point. Now we can actually, with our other information, with that sign chart filled in, we can actually say for certain. So this would be step 5. Finding the inflection points. All right, so our inflection numbers. Well, what were our possible inflection numbers? Well, we found these. These were x equals 0 and x equals 2. And now we need to check a few more things for each of these. We need to go through and check, is 0 in the domain of our original function? Is x equals 2 in the domain of our original function? Do we have a sign change at x equals 0? Do we have a change in concavity at x equals 0? Do we have a change in concavity at x equals 2? So we need to check both of these and see what happens. So let's go through x equals 0. X equals 0, we can plug it into this original function, and yeah, it is in the domain. Yeah, so this is a polynomial. So it's always defined. So x equals 0 is in the domain of this function. Same thing, x equals 2. This is a polynomial, so we can plug 2 in and get something meaningful out. So both of these are in the domain of our original function. The next thing we need to look for is a change in concavity. So let's go back to our sign chart and see, is there a change in concavity at x equals 0? Well, what happens? Here's x equals 0 right in here. And what's happening? On the left side, we're concave up, and then on the right side, we're concave down. So yeah, there is a change in concavity. We went from being concave up on one side to concave down on the other side. So yeah, we went from concave up to concave down. Okay. So that means x equals 0 actually is an inflection number. We do have an inflection point there. What about x equals 2? Let's see if we have a change in concavity there. So we go back to our sign chart. And where is x equals 2? Here is x equals 2 on our sign chart. And what we're seeing is that on the left side, we're concave down. And then on the right side, we're concave up. So yeah, there is a sign change here. We're going from concave down on one side to concave up on the other side. So yeah, there actually is another sign change or concavity change at x equals 2. So yeah, we go from concave down to concave up. So since both of these satisfy these extra conditions, our inflection numbers both of these extra or both of these x values, x equals 0 and x equals 2, They're not just possible inflection numbers. We're not just using them for our sign chart. They're actual inflection numbers. So we actually do have an inflection point there. So the last step then is to just figure out, okay, well, what is the y-coordinate for each of these? So let's find the inflection points. And this means just find the y-coordinates. So let's find the y-coordinate for x equals 0. What we're going to do is we're going to plug in x equals 0 just into the original function. So we have our original function here. Let's plug it in. And we get 0 to the 4th minus 4 times 0 cubed. We get 0. So this would be our y-coordinate, and the x-coordinate would be x equals 0. So 0, 0 is an inflection point. Let's find the y-coordinate for x equals 2. We'll call it y2 here, just to give it a name. What we're going to do is we're going to plug in x equals 2. So we're going to take our original function, plug 2 into it. So we get 2 raised to the power 4 minus 4 times 2 cubed. And what do we get? 16 minus 32. We get negative 16. So that means 2 comma negative 16 is also an inflection point. So these are our two inflection points. And there we go. Able to find the inflection points here. So the extra work here, why did we need to go through that sign chart? Well, we needed to actually verify first. These are possible inflection numbers, x equals 0, x equals 2, but there were a couple extra conditions we had to check. Both of these x values we saw were in the domain of our original function, so that was good. And both of them actually had a change in concavity. So that was the other kind of main requirement here. For an inflection point, there has to be a change in the shape, the change in the concavity. So both of these x values, 0 and 2, were inflection numbers. So then to actually find the point on our graph, we're just finding the y values and then writing them as a point here. All right, so not a bad little example. We're going to try another one that's a little bit more complicated, but still not too bad. So we'll see you there.